So if we have got some linear motion thing, I want you just to think of some suvat equations, because that's all they are. And then we're going to write them down, consolidate them, and then move on to rotational. So if you have a thing moving horizontally along a line, if you have something moving along a straight line, you know, or you'd be interested in, or you are told, or you can measure its initial velocity. Okay. You can also measure the final velocity if it is accelerating. You can then think about the acceleration. You can think of the time for the acceleration. You might like to think of the force which is responsible for its acceleration. What else crops up in linear motion? The mass of this thing, like that. So those are the quantities that you are familiar with when you do linear motion. Let me just check. U, V, A, and T. I forgot one. Displacement. So this thing moves a certain distance, S, in A time T. Right, there we go. So now I'm just thinking about those three in order. Displacement or distance in a straight line, velocity and acceleration. So those are the three that go together, and V and U, both velocities. T is the time taken for the change, F is the force, and M is the mass of the object. Okay, that you know. Did that in year, probably you might even have done speed as distance over time in year 7, for heaven's sake. And then you thought about accelerating things. So in year 10, you probably came across this acceleration thing. And then you did all your physics stuff and you got those suvat equations nailed. You've done a million questions about them. Totally, I can now assume, I hope, that you are 100% confident with them. Okay, because if you are, then I'm going to slightly arrogantly say, not arrogantly, I don't know what the word is, I'm going to now assume that you are totally okay with rotational motion, but maybe you don't quite get it yet. So look at that diagram there. There's something moving along horizontally up, moving in a straight line. Now I'm going to go kaboof. I'm now going to think of something rotating in a circle. Okay, rotating in a circle. So I'm going to now go through the same things. So what it's doing is it is starting here and it is going round an angle theta. Okay, just like the object moves in a certain displacement, a certain distance along a straight line, this thing is rotating through an angle theta. And let's say that it passes this point here with a at time t equals 0, t equals 0, and it arrives up here at t seconds. So it takes t seconds, t equals 0, t seconds. It takes t seconds to rotate that angle, like that. Okay, so what I'm going to do is I'm going to think of something which is analogous to velocity, going along in a straight line, but it's actually going round an angle theta. So instead of something going along at blah meters per second, I'm going to have this thing going round at a certain angle per second. Okay, so I'm going to call this, what should I call it? I'm going to call it omega because everybody else does. So omega is the angular speed, and that is the angle divided by the time taken, like that. Okay, just like something moving in meters per second, this is going at a certain angle per second. Now, the only slightly tricky thing is, what do we measure that angle in? Now, we could measure it in degrees if we wanted to. So I've drawn it there, maybe 60 degrees. Let's say it takes 2 seconds to go from A up to B. I could say that, so if I have theta equals 60 degrees and D equals 2 seconds, then omega equals 60 over 2 equals 30 degrees per second. Okay, fantastic, that'd be right. However, physics doesn't like that. No, I'm not going to say that. No. What we need is a different way of measuring angle, because the 360 degrees in a one whole rotation. It's not an arbitrary number, but it was thought up because 360 can be divided by 1, 2, 3, 4, 5, 6, 8, 9, 10, 12, lots of different numbers. What are they called? Factors or factors? They called factors? I can't remember. Yeah, I think they're called factors. That's why it was chosen. Okay. However, that is only because we like that sort of thing. Nature thinks of something better. So nature has come up, or physics has come up with a different way of measuring angle, and it's called the radian. And the radian does not have any units. That's its beauty. Now, a radian is, if I now do this in red, why can't I make this thicker line? Is that a bit thicker? Well, that'll do. So a radian is that distance there, the arc distance along the circumference, S, divided by r, which is the radius. So that is what theta is. Theta is now S over r, and that is measured in radians. S is measured in meters, r is measured in meters. Meters on top of meters cancel out. It is simply a ratio. That's why it's so beautiful. No units. Now, let's convert, just for the sake of it, let's work out what 1 radian is. So the unit of that is radians. Now you have, I'm sure, seen radians measure on your calculator. In an exam, if you are asked to do a question in radians, put your calculator in radian mode by pressing mode, I think, or something like that. And make sure that, there we go, and make sure that when you go back to doing questions about things sliding on ramps or resolving forces or anything like that, make sure you put it back in degrees mode, because a radian is not the same as a degree when you take sines and cosines of it, so it won't quite work. Now, let me see if I can do this. I haven't done this for some time. We have got 1 complete revolution, 360 degrees, all the way around, is equal to S, the path length, the circumference of a circle is 2 pi r, all the way around, divided by r, like that. So 360 degrees is 2 pi r over r radians. Okay, you've seen it, you've seen it. The r's cancel out. So I'm just going to divide by 2. 180 degrees is pi radians. And if you want to, you can do this. 180 divided by pi equals 1 radian, which is about 57 degrees. So 57 degrees is about 1 radian, like that. I think, actually, that's why I drew that. I said about 60 degrees. It's 57. So would you agree with me, if I squint at it for long enough, that S, the arc length around the circumference, so it's curved, is equal to the straight line radius between the center and where that circle is? Yeah, maybe. So that is 1 radian, if you ever cared. Okay, so let's just move on a little bit. No, let me ask you a question which somebody put onto the WhatsApp chat. Okay, so let's have this. We have omega equals theta over t, like that. So that is in radians. That must be in seconds. The units for omega, don't say W, it annoys me. The units for omega is the radians per second, like that. So a nice question would be an AQA. I've seen this as an AQA question. It would say something like, what is the angular velocity of a second hand? What is the angular velocity of a second hand? And omega equals radians. So a second hand, you've got to think of it going round 1 complete revolution. Okay. You don't have to, but that's sort of, well, obviously, if you don't mind me saying so, the easiest way of doing it. 1 revolution is 2 pi divided by how many seconds does it take to go around? It takes 60 seconds. Okay, so that is the angular velocity of a second hand. They tend not to do that. I think it was an hour hand, which is, so an hour hand is that seconds. That's put it into minutes. Seconds. Hold on a minute. Minute. No, that's it. That's it. Ooh, I was going to make an embarrassingly bad error there. So that is the angular velocity of an hour hand. That's it. Other questions I've seen: what's the angular velocity of the Earth in its orbit? It takes 1 year to go around once. Okay, so that's a sort of quite a nice basic sort of thing for angular. Oh, hello. Sorry, I missed that S. What's that S there? Sorry, I missed that. What was that? I missed it. Sorry, that was 9 minutes ago. Hey, John, I'm really sorry I missed that. Right, so can't remember what the question was. Anyway, thanks for using the chat. I really appreciate that. Right, now let's have a look at some of the things that we do in linear motion. So we've looked at the displacement of something in linear motion. We looked at, I'm going to say the next one up. Okay, if you're doing maths, we're differentiating it with respect to time. The next one up is velocity, which is that rate of change of displacement. Next one up, differentiating it, is acceleration is, I'm going to do that instead. I'm going to do that. Acceleration is rate of change of velocity, like that. And if you're doing maths, then I'm sure that you've differentiated these functions and sort of analyzed them more rigorously using differentiation. Anyway, so our feature S is, I've done it here. Our velocity, the linear motion equation is, velocity is change in displacement, rate of change in displacement, and acceleration is rate of change of velocity. Okay, what I should have put here is written displacement, velocity, acceleration. That's what I should have done. Now, in rotational motion, there are the same analogous equations. There are equations which are analogous to the linear motion one. So all you have to do is, in your heads, change the symbols. So instead of displacement S, you put the angle theta. Instead of V, you put omega, which is rate of change of angle. The acceleration is rate of change of omega, like that. So when we come to look at some equations, what I do in my head is I look at it and I go, rotational motion, not having anything to do with it. Thank you very much. And I look at all the things that they give you, and in my head, I convert them to linear motion. And I think, oh, they give me displacement, or they give me time, or they give me acceleration. And then I look at what they want, what the question's asking for, and then I shuffle all those things around in my head, and I write down the equivalent rotational motion symbols and the equivalent rotational motion equation. Okay, it's easy. So that's the analogous. Oh, here they are. So those are the analogous equations. There they are. Right. Next, for our linear motion, our suvat equations, we can do exactly the same thing. We can simply write out the suvat equation. So let's have this one. S equals ut plus a half a d squared. Let's have this one. V squared equals u squared plus 2as. Let's have S equals v plus u. NP. Eggshot, what's the NP there? What's the NP? I didn't see that happen. I'm going to move this. I'm going to move it.
No problem.
I should have got that. I'm sorry. Oh God, how embarrassing. How embarrassing. Of course it is. Okay. What's the other one? What's the other one? Is it this one? Hey?
V is equal to ut plus half.
Is it that one?
That's
no.
it? I was.
Give me another one. Give me another one. This is so
V
bad.
is equal to U plus AT. I
Yeah,
think that's it. Yeah.
yeah. So that's the bottom one. I've
Yeah.
done it. I've done it in a different.
Okay.
Oh, I'm messing up my lovely table. Okay, the linear motion equation is that. So all of these should go over there. Oh my God, I don't believe it. All of those should go there. And I don't know what goes on the left-hand column. I can't remember why I did this table. Who cares? Now, I'm going to do the equivalent rotational motion equation. S theta, the angle moved, is equal to the initial angular velocity times time plus a half. Now, the symbol for rotational acceleration is alpha, like that, t squared. Okay, so that is the equation that lets you calculate the angle that something has rotated if it's going at an initial angular velocity, but it is for some reason its angle, it's accelerating as it goes round. So it might start off slowly like that, then goes round and round and round faster. Okay, we've got this one, V2. So V2, the analogous is omega 2 equals omega 1 squared plus 2 alpha theta. Okay, I think you're getting the hang of this, and it's not very difficult. S equals theta equals omega 2 minus omega 1 divided by the time taken. Oops, divided by 2. Multiplied by, I must write meter, by the time t, like that. Okay, the next one, alpha. The acceleration is omega 2 minus omega 1 divided by t, the time taken. The same equations, And in fact, I can see the next slide coming up because it's them written out more neatly, and there are only 2 columns in this table. I think I'm going to adapt to my PowerPoint. So there they are. On the left, you've got the linear ones. On the right, you've got the rotational ones.